Let's talk about cryptography. Here is a very practical question, especially when you are embroiled in international espionage, or have something to hide from your wife: how to send a secret message so that only the recipient can read it, while for anybody else the message will be unintelligible. Of course, we have to use some coding method. We have to encrypt our initial message, so that the result will be a meaningless string of letters, and then the recipient has to decode it using an appropriate key in order to restore it to its original form. The simplest way to achieve that is based on the so-called Caesar cipher allegedly used by Julius Caesar in his private correspondence. The Caesar cipher is indeed rather unsophisticated. You take every letter of your message and shift it by a secret number of places in the alphabet. For instance, shifting all letters by 3 places will replace the letter A with D, B with E, and so on. When you get to the end of the alphabet, you go back to the beginning, so that X is replaced by A, Y by B, and Z by C. Breaking this type of code is child's play. There are only 25 possible shifts you can perform, so you apply every possibility to the encrypted message and see if the result makes sense. Even plausibly more sophisticated keys can be broken, if only each letter of the alphabet in the original message is consistently translated into the same letter. Thanks to that, we can make use of the known facts about the relative frequencies of letters and combinations of letters in the English language, and on that basis we can guess what the encrypted message means. For instance, we can use the fact that the most common letters in English are E, T, A, O, and that the bigram TH is also very common, to plausibly estimate which letters in the coded message represent the original ones. A better way to encrypt messages is known as the Vigenere cipher. First, to make things more mathematical, we associate with every letter a number. Letter A has the number 0, B, number 1, and so on. Then we select a random text, called the key, for instance the first sentence from some book. Note also that the key may be a string of random numbers rather than a text. Taking the message to be encoded, we add to the numerical value of its first letter the numerical value of the first letter of the selected key, and write the letter corresponding to this number. If the number is greater than 25, since there are 26 letters in the English alphabet and we started counting letters with 0, then we subtract 26 from it. This is known in mathematics as addition modulo 26, so for instance the result 26 translates into 0, which is A. Then we repeat this procedure for the remaining letters. To do that, it may be convenient to use a disk with 26 letters placed on the rim in alphabetical order. In order to encode the first letter of your message, you rotate the disk clockwise by n slots, where n is the number corresponding to the letter in the key, and then you take the letter that occurs in the slot previously occupied by the letter to be encoded. The crucial difference between the Caesar cipher and the Vigenere cipher is that in the former every letter in the message has consistently the same translation for all its occurrences, while in the Vigenere cipher the same letter of the alphabet can be encoded with the help of different letters, depending on its place in the message. That way we scramble the information about the relative frequencies of letters in the original message. The resulting garbled string of letters can then be deciphered by a person who knows the key. The decoding procedure is a reverse of the encoding one. You rotate your disk counterclockwise and read appropriate letters. The trouble is, though, that whoever captures the key can read your messages. So the method is only as good as the security of the key. But there is a solution, well, at least a partial solution, to this problem offered by the mathematics of prime numbers. The key fact here is that the prime factorization of large numbers is a very time-consuming, complicated process, while multiplying 2 numbers is relatively easy. This is an example of what is called a trapdoor function, a function that works nice and easy in one direction, but is very hard to perform in the opposite direction. The way this works in the case of cryptography is roughly as follows. The sender of the message possesses a very large number n that is used to encrypt the message. However, in order to decipher the message, 2 prime factors p and q of n are needed. These factors are only known to the addressee, nobody else. The sender can publicly announce his or her key number n, without fearing that an unauthorized person will decode the message, since the factorization of n is practically impossible. And because the sender doesn't even know the factors p and q, the risk of capturing these keys is minimized. There is a different, rather clever way to avoid the danger of capturing the key. The idea is to use 2 keys, one known only to the sender, call her Alice, and the other used by the recipient, Bob. Alice takes the original message, encrypts it with the help of her key, and sends it to Bob. Then Bob encrypts the already encrypted message further with the help of his key, and sends it back to Alice. She then decodes the message using her key, and as a result the message will remain encrypted only by Bob's key. Finally, the message gets sent to Bob, who uses his key to decipher the message and reads it. Pretty awesome, isn't it? This method completely avoids the need to exchange keys between Alice and Bob, and therefore prevents an eavesdropper, call her Eve, from capturing them and deciphering the message. And all messages sent over public channels are encrypted, so Eve can't read them without a key. However, there is a catch here. For this method to work, the encoding procedures using different keys must commute with each other. This means that combining the operations in different orders yields the same result. In our case, the requirement is that regardless of whether Bob encrypts the message after Alice, or Alice after Bob, the outcome should be the same. Why? Because we have to make sure that when Bob sends to Alice the doubly encrypted message, her action will undo her previous encryption so that the result will be as if the message was only encrypted by Bob. Let us write this down using some symbols. Let M denote the original message, Ka the operation of encryption using Alice's key, and Kb encryption by Bob's key. Let us also symbolize the decoding operations using appropriate keys as Ka bar and Kb bar. Clearly, applying the operations of encoding and decoding in succession should recover the original message. Note that the order of performing operations in this notation is from right to left. The first operation done on message M is the one that stands closer to M. Now, the message after Bob's encryption will be given as KBKA-M. If operations KB and KA commute, we can rewrite this as KA-KB-M, and then when we apply Alice's decoding procedure we will get Ka bar Ka-KB-M, which equals KBM, since encoding and decoding with the same key done in succession cancel each other out. But this is not guaranteed when the operations Ka and Kb don't commute. Even though, generally, different coding keys do not commute, the Vigenere cipher is a happy exception. This is easy to see. For each letter of the original message, a particular key determines the number of slots that we have to rotate our disk by, to encrypt the letter. But rotations of a disk commute. Rotating first by 3 places and then by 5 is the same as rotating by 5 and then by 3 places. In both cases the outcome is a rotation by 8 places. So the method described above would work. Unfortunately, the commutativity of the encoding procedure creates a vulnerability that can be exploited by Eve. Suppose that she captures all 3 transmissions between Alice and Bob. Now she can take the second message encrypted by Alice and Bob, and subtract from it the numerical values of the first message before Bob's encryption. That way she will obtain Bob's key. Similarly, by subtracting the second message from the third one she will find out Alice's key, and the game's up. The inherent weakness of the Vigenere cipher is that if you get a hold of a message and its encoded version, then you have the key with which the encoding was done. One possible way to eliminate the danger of eavesdropping is to invent an early warning system. That is, if Alice and Bob could learn instantaneously that Eve is listening in on their conversations, they would immediately break up the connection and try some other time. But how to detect that the transmission was intercepted by Eve? Here quantum magic can help. There are 2 fundamental facts regarding quantum interactions that play a crucial role here. First, any act of observation, measurement, unavoidably disturbs the observed object. More precisely, measurements affect the state of the measured system, causing it to collapse into one of many possibilities. Consider a simple example of a chair that can be found in one of 3 places: your office, your kitchen, and your neighbor's bathroom. According to quantum mechanics, before your act of observation, the chair may be in a state of superposition of these 3 places. But you can't see a single chair in 3 places at once, so the moment you look, it materializes, for instance, in your kitchen. The act of observation forces the chair to change its state from an undetermined to specific. The second feature of quantum reality that can be exploited in communication is known as non-local quantum correlations. As it turns out, it is possible to prepare 2 or more quantum particles in a state, known as entangled, such that no matter how far away the particles are, measuring a quantity on one particle changes the state of the other one in correspondence with the result obtained locally. Taking these two things together, it is at least theoretically possible to transmit the key between Alice and Bob using entangled quantum particles, for instance photons, in such a way that if Eve intercepts some of these photons and check their states to learn the key, Alice and Bob can tell by measuring their photons. This method is known as quantum communication, or more accurately quantum key distribution. Whether future communications will use these quantum effects as a safety measure remains to be seen. For now, this is just an exciting theoretical possibility. Current cryptography relies more on mathematics than on quantum physics. As we pointed out, prime numbers play a central role in modern ciphers. Why? Because finding large prime numbers is extremely complicated, and only the most powerful computers in the world and the cleverest algorithms can push the boundary and calculate previously unknown prime numbers. According to Wikipedia, the largest prime number known so far, as of July 2026, has 41,024,320 digits. With prime numbers we have another interesting case of a gap between what we know as theoretically possible and what we can achieve in practice. Since the times of Euclid, we have known that there can be no upper limit on prime numbers. For every prime number there must be an even larger one. But we have no simple formula that could calculate larger and larger prime numbers. Of course, you can always try to find successive prime numbers following a long and tedious road. For any number, try to divide it into any of the preceding prime numbers. If the result is whole, the number is not prime, but if there is always a remainder, it is a prime. Good luck with that. Soon the computations will grow to such enormous sizes that all the computers in the world taken together will not be able to finish them during the lifetime of the universe. Fortunately, there are some tricks that can be used to substantially speed up the procedure. One of these tricks is based on Fermat's little theorem. The theorem states that if n is a prime number, then taking 2 to the power of n and subtracting 2 from it will produce a multiple of n. This seemingly insignificant fact is of great help to those who are in the business of finding prime numbers. It offers us a relatively simple method of eliminating numbers that cannot possibly be prime. If we find out that 2 to the power of n minus 2 is not a multiple of n, we know for sure that n is not prime. And calculating the value of 2 to the power of n even for large numbers n is within our capabilities. You can find out how to prove Fermat's little theorem in this book, available on Google Play.